Good morning, everybody. Today we are discussing the next topic of the nuclear chemistry, that is the binding energy of the nucleus. In the last class, we have discussed the mass defect. Mass defect is the mass difference between the sum of the mass of the nucleons of the nucleus and the actual mass of the nucleus. But this difference is known as the mass defect, and this difference of the mass defect is mainly due to the formation of the binding energy or the attractive force which is existing between the nucleons inside the nucleus. So we can calculate this binding energy by using the Einstein mass energy relationship. So we have already studied the Einstein mass energy relationship is E is equal to mc square. So for calculating this equation for binding energy, E is representing the binding energy in terms of joule, and m is the mass defect in kg, and c is the velocity of the light, that is 3 into 10 to the power 8 meter second inverse. So we have to study the definition of the binding energy, that is very important, the frequently asked university question. So that is the energy released in the formation of the nucleus from its component nucleus is called the binding energy of the nucleus. Then what is the role of the binding energy? So the importance of the binding energy means the binding energy is directly proportional to the stability of the nucleus. As the binding energy of the nucleus increases, the stability of the nucleus is also increases. And we know that some amount of the energy is required to bind the nucleons, that is neutrons and protons inside the nucleus. So that energy is known as the binding energy, and this much amount of the energy which is equivalent to the binding energy is required to destroy this same stable nucleus. So the binding energy is equivalent to the energy which is required to destroy the nucleus. So that is the importance of the binding energy. Now we have discussed the Einstein mass energy relationship, E is equal to mc square. But in this equation, mass is expressed, that is mass defect is expressed in terms of kg. But in some time in problems, mass defect is expressed in terms of AMU. So there is a relationship is existing between the AMU and the kg. This is the relationship. 1 AMU, that is 1 atomic mass unit, is equal to 1.66 into 10 to the power minus 27 kg. This relationship is very important while we are doing the problem of the binding energy. So we have to by heart this equation. Now we are moving into next conversion. So we have already discussed the E is equal to mc square, where m is expressed in terms of kg or in terms of AMU. If you are directly substituting the mass defect, that is delta m, in terms of AMU, there is a relationship is existing between AMU and energy in terms of million electron volt. 1 AMU is equal to 931.5 million electron volt. That means if you are substituting the mass defect directly in terms of million AMU, we will get the energy in terms of million electron volt if you are multiplying by 931. That means if mass is known in AMU, we have to just multiply it by the term 931.5. You will get the binding energy in terms of million electron volt. These two relationships are very important while we are doing the problem. So 1 AMU is equal to how much at kg, and 1 AME is equal to 931.5 million electron volt. These two relationships we have to by heart. And the binding energy, both the statement is very important and the problem is also important for the university question. Now we are moving into the next title, that is the binding energy per nucleon. So binding energy per nucleon, the title indicate that we have studied the binding energy for the nucleus, for the entire nucleus. So this nucleus is formed by the combination of the nucleon. So per nucleon, how much is the binding energy? That is the binding energy per nucleon. So the definition is the binding energy per nucleon is the total binding energy of the nucleus divided by the total number of the nucleons in the nucleus. So the binding energy per nucleons in terms of equation is total binding energy of the nucleus divided by the number of the nucleons in the nucleus. So greater the nuclide, having the greater value of the binding energy, which is around 8 million electron volt per nucleon. So now we are moving into a plot. See here, this is the plot of the mass number against the binding energy per the nucleons. So here we can see that the mass number from 50 to 220, majority of the nucleus are belonging to the one line and having the binding energy per nucleon is 8 million electron volt, in between 7 to 9 million electron volt. That means these nucleus are stable nucleus. See here, iron it is 56 and chlorine, yttrium, arsenic 75. These are the some of the stable nucleus and which are belonging to the binding energy per nucleon is equal to 8 million electron volt. But when we are moving downwards to the 50, that is the atomic mass from 0 to mass number 50, the mass defect is little bit lower than that of the 8. So these the 8 million electron volt is the stable nucleus. From that, the stability of the nucleus is little bit lower. This shows the graph. So for the lithium, the binding energy per nucleon is only the 5.2 million electron volt. That means the nucleus is highly unstable according to this concept. So now we are moving into one of the example. In the case of the helium, the binding energy of the nucleus is 28.3 divided by 4, that is the total number of the nucleon which is present in the nucleus. So we will get 7.1 million electron volt. That is binding energy per nucleon is 7.1 million electron volt, which is close to 8. That means this helium nucleus is highly stable. I hope that you understood the concept and the definition of the binding energy and binding energy per nucleon, and the problem is also important, and these questions are frequently asked question for the university question. Thank you.